optimization techniques, and hybrid quantum classical approaches. We'll then explore applications in machine learning, current challenges, industry pilots, research opportunities, and finally a future outlook before a question and answer session. Let's try to make the session today a bit more interactive. I would appreciate more questions coming in from the team. Am I audible, Dr. Rosna? Is it okay? Yeah, perfect. Sorry, it's kind of a rain here. Probably that's the reason. Okay. I hope there are no background disturbances, right? Yeah, thank you. Thank you, Doctor. So, from the introduction to quantum computing aspect, let's start with a quick refresher about yesterday as well, with a quick refresher on what quantum computing is. Unlike classical bits, which are either zeros or ones, qubits can exist in multiple states. We already discussed this yesterday. And thanks to this superposition, wherein qubits are becoming extremely faster compared to the classic computational technologies, and when qubits interact, they can be entangled, enabling correlation for stronger than classical systems. This makes quantum computers uniquely suited for solving complex optimization problems where the number of possible solutions grows exponentially. And since optimization is at the core of machine learning, you can already see why this is such an exciting overlap. If we talk about quantum principles, the superposition, entanglement, and the interferences which are being solved using the qubits are uncomparable compared to the classical bits. Mostly, the power lies in solving the complicated and computed solutions, wherein this technology takes an upper hand from the computational aspect. The motivation here is machine learning is optimization, which is heavy prime for quantum advantage. If we talk about optimization in machine learning, optimization is really the engine of machine learning, as I have stated earlier. So, if you say optimization, this is the heart of machine learning, or this is the engine of machine learning. Every time you train a model, you are minimizing a loss function. Now, why a training is required, a model training is required? Because machine learning, we are talking about training the machines with more and more models across digital image processing, models across any algorithms which are used for security purposes, data transmission purposes, computational purposes, or prediction and I can say forecasting purposes. It can be any kind of a model related to any different domain. So here the model trainings plays a very critical role. If we are training a model, that means we are minimizing the loss function. And this is an iterative cycle. The models are trained regularly to a state where they deliver the desired result, and once the training is done, the output of the model is being again correlated with a next set of parameters, and then the training begins again. So this is a continuous process, which we call it CI/CD, which is like a continuous interaction and continuous development process, a CI/CD model. Based on that model only, the models are trained. There are hyperparameter tuning which is involved to find the best architecture from the training aspect. And the feature selection is also critical to reduce the dimensionality. Now, even selecting features is an optimization problem, because you cannot have unnecessary features expected from a model which is required for another different purpose. There are models for if we take an example from the from an organization perspective, where a company like a burger company who is trying to sell a lot of burgers and pizzas on their retail chains, if they are planning to predict their sales for the next 6 months, then this prediction comes with an algorithm. You cannot have the same prediction being applied regularly. The prediction has to be tailored, has to be modified based on the climate, based on the time of the year, based on the present, I can say, the conditions across the city or across that specific geographic location and all, and that is where the desired results comes into picture. There are certain models across digital image processing where you might have already seen the effect of AI and ML. If you give the image of a young boy, it directly gives you the output how that specific boy or a girl might look in the old ages. So these are all been using a different set of algorithms continuously, and then coming to a desired result based on the parameters. So the parameters here plays a very critical role. If I am giving a parameter like, okay, give the specific forecast based on a boy or a girl's picture who is staying in Africa, then the output is going to be different. In another scenario, if I give the parameters, say for example, give me the this boy or a girl how they looks like probably in old ages in, say, geographic location in China, then the output is again going to be different. So the hyperparameter tuning or the parameter combination plays a very critical role in terms of optimizing a machine learning model. Now, as we discussed already, there are classical challenges also which are associated. The challenges like non-convex landscapes. These landscapes are often non-convex, filled with local minima. High dimensional data adds even more complexity to it. And moreover, with modern deep learning models, the computational load becomes enormous. Now, when we say model deep learning models, this is exactly the scenario which is happening these days. If we talk about the number of subscribers which are connected to a specific in telecom company, for example, a company like Airtel is serving 1 million subscribers in a specific location, then the computational capacity, it has to be at a different level compared to the computational capacity what it had been in the last decades. So this and not just that, even that computations are coming with deep machine learning models. Applications like Airtel, the applications like other telecom service providers, they are directly processing the data, a huge data on a daily basis, and then coming up with certain results. Again, this is all parameterized. It is getting driven with a lot of data behind it, and that's why researchers are looking to quantum computing to potentially explore these spaces more efficiently. With modern deep learning models especially, the computational load becomes enormous. You might have seen, okay, there is a new feature which is, for example, added by Airtel. If someone calls you, it is giving you a warning that it can be a spam. Now, how does that come into picture? The frequent calls which are made from a certain number, from a certain mobile phone number, are being read by the algorithms. It captures the voice communication which happens over that specific channel, and if it sees like a kind of an advertisement related words, or it sees any such kind of, say, marketing related activities, or any junk call related keywords are being captured in that discussion, then automatically, based on the frequency of the calls which are being made, those numbers are being stated as dormant, or they are considered as, say, spam numbers. So this is all happening because of the outputs which are coming in from more and more advanced machine learning models today. Quantum so in order to address such issues, there are different quantum optimization techniques available. We'll talk about mainly four different techniques. We have got quantum approximate optimization algorithm, QAOA. We have got quantum annealing, and then we have got quantum gradient descent. We have got quantum support for convex optimization. Let's take the first one, quantum approximate optimization algorithm. It has got a variational method for combinational optimization. It offers some powerful new tools, it's one of the most promising. It is designed to solve uh, combinatorial optimization problems and has direct applications in machine learning. Next, we have got quantum annealing. It is implemented mainly in D-wave systems. It mimics physical annealing processes to find low energy solutions. We have got quantum gradient descent. It can accelerate training by leveraging quantum linear algebra. That's something interesting. And algorithms like HHL can provide exponential speedups for solving linear systems, which are the backbone of many machine learning models. While not all of these are practical today, the theoretical foundations are strong, which from the machine learning perspective. There is a comparison also. There is a comparative chart available, which you can see over here. Okay, let's take this quantum optimization techniques. If we try to measure a technique based on the core idea, the QAOA, the first quantum approximate optimization algorithm, it uses a parameterized quantum circuit alternating between problem Hamiltonian and mixer Hamiltonian to approximate solutions. Whereas the strength of this specific technique is that it is well suited for combinatorial optimization. It can run on NISQ devices and it's flexible and tunable as well. We have got limitations also, just like any other technique. The limitation of QAOA is that it requires parameterized optimization. The performance here depends on circuit depth. Also, the key applications or the practical examples of QAOA is the portfolio optimization or scheduling or logistics mainly. This is where the QAOA comes into picture. We have got quantum annealing. This is another optimization technique. The core idea behind this technique is it explores energy landscape by slowly evolving from an initial to problem Hamiltonian, finding global minima. Now, the strengths for the quantum annealing, unlike the first technique, is that there are ready hardwares available for such kind of optimization techniques. It is good for certain optimization landscapes naturally suited for icing cubo problems. If we talk about limitations for quantum annealing, we've got it is limited to specific architectures only. It may get stuck into local minima, less generalizable, because you cannot, as I said in the beginning, it all depends on the parameterization comes into picture from the optimization perspective. So more specific parameters has to be given when we talk about the annealing technique. They cannot be general parameters which are associated from the output oriented desired results. The key application of quantum annealing is the supply chain, the traffic optimization mainly, material science and all. When you say traffic optimization, like for example, let's take a physical example of a traffic signal at an X road. You have to have a specific parameter given, like what is the traffic coming in from a specific route, and then what are the available outputs for that specific traffic, and then based on that only the predictions can come into picture. So such traffic optimizations can be done only with a more specific parameter. That's why the limitation here lies. It says that it is less generalizable. So generalization cannot be done with a technique which has been mentioned in the point number 2. We have got VQE, another famous optimization technique. We are talking about variational quantum eigensolver for optimization. It uses hybrid quantum classical optimization loop to minimize energy functions. It reduces hardware requirements, flexible to adapt to different problems. That is the strength about the VQE technique. It is very much flexible to adapt to different problems. That is why the key applications here are machine learning, hyperparameter tuning, chemistry optimization, and such kind of a thing. There are lots of permutations and combinations can be made, and desired output can be generated using the VQE technique. We have got Grover's search algorithm for optimization. We generally call it GSAC. Here, the quadratic speedup for searching unsorted data or solutions is the core idea behind it. The strength here lies that it provides theoretical speedup. It is useful for discrete optimization. But again, here it needs more qubits. When you say it needs more qubits, it needs more powerful computational systems, and it is limited from the practical hardware implementation today, because not every organization or a sector can have this high computational servers available with them. For a high kind of computational methodology, then such kind of an infrastructure has to be present, and then based on that infrastructure only the key applications onto the database can be made. When we say database search, pattern matching, such kind of key applications can be easily achieved using the Grover search algorithm. And huge data sets, which can be like an organized data set, an RDBMS, or it can also be like a general unstructured database, which can be like a search engine related to Google, or a search engine related to a specific organization, or any such thing. So such database searches are the key applications from the GSA technique. Lastly, we have got quantum gradient descent. Here it extends gradient descent using the quantum properties to accelerate convergence. It all stays the same, as the limitations from this specific technique is that it is still in the experimental stage today. The results are not trusted compared to the other optimization techniques. Moreover, neural network training, which we are talking about, large scale machine learning optimizations, which we are talking about, hyperscale models for forecasting, prediction, which we are talking about, can be the right applications from the quantum gradient descent uh, algorithm perspective, or the technique perspective. To give a summary of this window, if we sort them into five different categories from the technique, type, use case, hardware, and scalability perspective. The first technique, QAOA, it is a gate based technique. It uses the case, which we call it graph problems, that is, and clustering. This is the machine learning use case for this specific technique. And of course, from the hardware requirement perspective, we need NISQ devices here, with moderate scalability. For the VQE, when we see VQE, we are talking about variational quantum Eigenhover technique. Here the type is hybrid. When you say hybrid, okay, it's a combination of both analog and the gate based technique. And then model training and feature selection are the machine learning use cases associated with VQE. Hardware requirements, again, NISQ devices are required. Scalability is very high from the VQE aspect, as I have told in the previous slide. We have got annealing technique. It is an analog of type. And then the optimization and scheduling kind of a use case is applicable for the annealing technique.
இப்படியே தான் பண்ணுவாங்க மேம் இங்க பாருங்களேன்.
The
எங்க
hardware
வீட்டுக்காரர்
required
கூட்டிட்டு
is
போய்
D-Wave,
வச்சிருந்தா
and the
கூட்டிட்டு போய் விளையாட
scalability is
பண்ணுவாரு.
very limited here.
எங்க வீட்டுக்காரர்
Scholars, can you please mute your mic? Thank you. I hope the quantum optimization techniques are clear. Let's move on to the hybrid quantum classical approaches now. When we say classical approaches, because the current quantum devices are still noisy and they are little limited, compared to the previous ones, most useful applications, they come from hybrid approaches. One famous method is the VQE, as I have previously stated, the variational quantum eigensolver, or VQE. Here is how it works. The quantum computer explores possible solutions, while the classical computer evaluates and guides the optimization process. If you talk from the application aspect, the quantum computer, how it solves, it gives the solutions from the possible exploration aspect. Whereas how the classical computers, it had been evaluating and guiding the optimization process. It is not executing, it is only evaluating and guiding the process. This loop leverages the strengths of both the systems. Especially the hybrid models are practical today and allow us to experiment with quantum optimization on real problems. And if you say hybrid loop, you've got quantum processor, which is exploring solution space. You've got classical processor, it evaluates cost function. Let's go into something from the application aspect in machine learning from the quantum perspective. In training models, for example, quantum optimization can accelerate algorithms like logistic regression or SVMs. These are the training models which are faster today They are much complicated, but computationally they are very sophisticated compared to the classical techniques. And from the neural network training aspect, we have got gradient optimization using QAOA, which we have already discussed. QAOA as a technique, in especially for neural networks, this is where it becomes handy, and it can reduce the training time also, because it's not easy for a model to be trained. For training a model, again, you have to provide that many number of parameters to, and that many number of combinations to a specific model. So providing a combination is not a manual process. There has to be that many combinations prepared in advance and has to be injected against an algorithm. And this is how the based on the expected output, if the linear output is coming on quite expected, then only the next set of combinations can be applied to it. In supervised learning, especially algorithms like quantum k-means or quantum PCA, it helps with clustering and dimensionality reduction. Clustering and classification from the quantum k-means aspect, again, it's kind of a real application from the perspective. Reinforcement learning, as we all of us know, this also can benefit from quantum assisted policy optimization. From any kind of a reinforcement algorithm, the quantum methodology, the machine learning methodology can come into picture. And in generative AI also, we are exploring quantum Boltzmann machines, for example, which could open up new possibilities in the data generation. This is where things start getting really exciting. Generative models, and as we have just discussed about an example, it's a generative model wherein parameters for a specific image are being given at a specific age, say in the young age or the childhood age. And then based on that model, the algorithm is generating from its deep learning capability the output how that boy or that girl might look in future, say in 70s or in 80s or in 90s. So this transition from one stage to another stage is generated using these generative models. And again, the implications can come in only from the quantum Boltzmann machines, which are computationally rich and fast enough to compare and give such kind of a output, and based on that output the data transformation can only be happening. Let's move to current limitations and challenges from the computational aspect. Of course, the when we talk about quantum computing, current quantum devices have only a few hundred qubits, and they are highly noisy as well. So it's a huge hardware constraint because of limited qubits available from the computational aspect. The speed is also going to stay limited. The more and more qubits getting added can have a much faster implication from the output generation perspective, and at the same time the noise also gets increased. So there has to be a balance. There has to be some sort of, say, some sort of solution to be applied to have the noise getting reduced by applying any kind of a filter from the computational aspect or whatever it is. Next is error correction. This is still experimental and resource intensive. Error correction is possible, but it is extremely resource intensive, because the errors can be corrected only when you identify them as an error, because we are kind of predicting the we are using the algorithms from the prediction aspect or from the forecasting aspect, from the generative AI aspect and all, or from the conversion of the data aspect, converting one form of data to the other form. We still don't know what the other form can look like, or we still don't know is the desired what is the exact result is. What we all know is just a desired result. So comparing an exact result with a desired result, this is where the error correction can happen. So that kind of correction methodology has to be in place to minimize the error, and at the same time to marginalize the deviation which is happening, the error correction plays a very critical role. And this is again another self learning and self optimized kind of a quantum algorithm to reduce the error margin from the input to the output perspective, or from the desired output to the actual output perspective. Next, we've got scalability. It's hard to scale algorithms to the real world data sets. Many algorithms don't yet scale to the size of the real world ML datasets, just because the desired result data can vary, and that resulted datasets are again difficult to be handled on the based on the capacity of the hardware which are associated with them. The theoretical models are ahead of the hardware, of course, but again it becomes little difficult. Algorithm maturity, many techniques still theoretical, but those techniques are ahead of the hardware, because theory can have a lot of formulas, it can have a lot of prediction based on a specific formula or a specific algorithm, but the actual implementation, this is where the scenarios changes based on the different factors which gets associated during the execution of a specific model. Finally, there is a major skills gap also. We need for quantum aware data scientists and ML experts. So while the potential is immense, we must be realistic about where we stand today, like how familiar we are from the algorithm perspective, how familiar we are from the techniques perspective, which we have just stated about, and how familiar we are from the desired result aspect, so that we can have the self-driven error correction associated with them. Let's move to the next slide, industry pilots and use cases. Industry is actively experimenting. We have giants like Google, IBM, D-Wave, Xanadu, pharma industry, and all, who are processing a lot of computational power, who are using a lot of computational power, especially Google. Okay, they has tested quantum machine learning algorithms for image classification. Earlier you might have seen, like in the last decade, there was only the search option available, that too with a minimalist features. Today you can do a search using an image, and that image to image comparison is happening within a millisecond of a time. This is all coming in from the quantum computing. Not just the quantum computing, but also from the quantum ML algorithm aspect. So the algorithm is reading that data, again an unstructured data. You can give an audio input, you can give a video input, you can give an image input, or you can give a text input, that too in discrete languages across the globe. Still they are able to capture the data, take it as an input, process the data in the algorithm, and give it to you, and give you the desired output. Now this is not just the end of the story. The beauty lies in the algorithms security policy, and in the algorithms delivery engine also. It is not just giving you, I can say, unsecured images. It is not giving you unrealistic images, and also at the same time it is not giving you unsocial images as well. It is taking care of all those filters to be applied, and at the same time it is also taking care of the geographic aspect from the user's input parameter perspective. So this is all happening within a millisecond, within a millisecond of a time. You can imagine how many qubits might be parallelly running once a user input goes inside the processing engine. We have got the example of IBM also. IBM has launched, Qiskit machine learning library, which is available for the developers. Now this is where especially the scholars, the developers, they can start using such a machine learning library to apply onto the activities which they are associated with. There are libraries associated for all different sort of I can say implications into any different vertical and segment of the industry, for pharmaceutical industry, for healthcare, for hospitality, for retail, for aviation industry, for defense and logistics. So it's like a huge ecosystem which has got n number of libraries already available. So it's just a matter for a developer to pick the right one and start moving on further for that specific algorithm. Next, we have got D-Wave. D-Wave is applying quantum annealing to feature selection and portfolio optimization. We've got Xanadu. Okay, it's working on photonic quantum computing for generative machine learning. And then the pharma industry, pharma companies are exploring drug discovery with quantum enhanced models. When you say drug discovery with quantum ml optimization, they are like trying to predict, you might have already seen in the news these days. Now they are trying to read the development of a cancer cell, how it can look probably in the very early stage, and how it can grow up considering the status or the age or even the health of that specific patient. So if you give the right set of input parameters to that specific algorithm, it can give you the prediction, okay, yes, is it really a cancer cell or is it just a normal infected cell which is looking like a cancer cell. This is where the ml algorithm tuning comes into picture. If you are tuning that algorithm with more and more inputs and with more and more parameterized conditions, then you will be able to benefit it out from that machine learning algorithm to give you the desired result. And this is going to be a game changer again from all different aspects. It is kind of reducing the threat associated with a human's life. It is reducing also the duration of the treatment. Certainly, if you go ahead with a preventive methodology rather than going ahead with a corrective methodology, prevention, it always desires or requires less resources compared to the corrective methodology. Corrective methodology comes into picture when you have already seen the impact of those cells. Those cells have already ruptured, they are already in the damaged state, and this is where a surgery might need to be performed, or whatever the implications are, those needs to be handled. But from the preventive aspect, suppose if the algorithm is predicting that, okay, yeah, these are the dangerous cells in the initial stages, probably with a mere simple medication these things can be easily addressed. So this is how you see how the use cases and applicable algorithms are there from the industry aspect today. There are more and more use cases and more and more industry pilots you see today from the quantum ml algorithm aspect. I would be more than happy, in fact, to get in touch with you all for such discussions across such use cases on such algorithm development processes and all into very discrete segments. We are talking about manufacturing, industrial automation, aviation, retail, healthcare, medication, or whatever this the segment we are talking about. There are the practical implications or the applications associated with those machine learning algorithms. Let's talk about the research opportunities which are available for the students today. From the research opportunity aspect, no, this is the best part for you as student. This field is wide open, as I said, wide open. There are a lot of designing new quantum inspired optimization algorithms which are still available today, which the students they can work upon. They can come up with the expected results or the desired results, and then comparing those desired results with the actual results, and then calculating the deviation, training the model again comparing the output versus the actual versus the desired. Again, if you see a lot of variation, again do another round of iteration. So this is the process or the place wherein the scholars and the research scholars or the students they see the opportunity today. Another thing, adapting machine learning models to quantum hardware as well, because with the ml algorithm associated, okay, the execution also has to be on that respective hardware. You cannot have such complicated algorithms running on simple hardware infrastructural elements. There has to be a high computational aspect associated with it, and for that perspective only, the high end or the top end hardware quantum computing devices comes into picture. Again, another opportunity is developing hybrid frameworks that balance quantum and classical strengths, because remember, this is an era which is a transformative era. Okay, you are talking about the users who are doing computations using their legacy devices like laptops, desktops, or maybe some high end servers, and we are talking about the computational devices which are used by giant engines like Google, IBM, and all, who are training those algorithms. So there is a transfer, so it's a transformative phase. During this transformative phase, exploring new hybrid frameworks from both the ends could be the real world application for the research scholars. Next, investigating quantum kernel methods for SVMs and clustering, another very good application. Then building error resilient machine learning techniques. As I've already emphasized earlier also, error resilient techniques plays a very critical role. The margin of error, or the deviation of the desired result versus actual result, plays a very critical role. The less the deviation, the less the errors from your ML technique aspect. Then interdisciplinary research, quantum plus AI plus physics plus math. So this is like things are connected with each other. The humans, or the computations which is like really impossible for a human to be done, can be done very easily using the computational techniques in a millisecond of a time. This is what something about research opportunities which are available for the scholars today. And not just this, there is a future outlook also which is associated from the same aspect. If we look ahead, say for example 5 to 10 years from today, we'll likely see hybrid quantum classical machine learning becoming practical for optimization problems. And why it is becoming more and more familiar from the practical optimization aspect, because it will be more heavily used. Today you're just talking about few of the use cases into a specific industry. Tomorrow those use cases becomes a general use case, and then the execution layer of that use case shifts from the service providers to the consumers, and this shift will require a lot of awareness by the users, and at the same time awareness by the people who are going to execute it, and also an awareness by the developers who are going to develop such an algorithm. So 5 to 10 years from today, you'll see the practical hybrid quantum ML for optimization problems. Similarly, 10 to 15 years, the fault tolerant quantum systems scaling to larger data sets. Why we are saying fault tolerant quantum systems? Because as I said, not it's not easy for the desired results to be generated at the same time. There has to be a numerous iterations to be done with a discrete number of permutations and combinations of the inputs, and then only the desired results can be fine tuned, can be optimized using any of the machine learning optimization techniques. Quantum ML won't replace classical ML, this is for sure, and this will in fact, it is in fact going to complement it, offering acceleration where classical methods they struggle a lot. So quantum machine learning, it's let me make a very clear statement: it is not a replacement of the classical machine learning. It is only adding a value to it by providing more and more computational approaches, more and more possibilities from the computational aspect, and more and more combinations of the input data, so that the output stays with the desired results. Major impact areas are healthcare, finance, logistics, cybersecurity, climate modeling, and other things. The industries most likely to benefit include all these different categories. And then not just that, even from the business implication aspect also, the future outlook of ML for quantum computing algorithms is really good. Now, the key takeaways, if we talk about, to summarize the discussion today, machine learning is optimization heavy, and quantum offers natural advantages. So the combination is really powerful. You've got a deep learning, learning data models from the machine learning aspect, and you've got the optimized engine from the hardware aspect, and this offers a natural fit to have an excellent combination of two peak technologies, giving you the solution to the desired problems. Algorithms like QA, OA, and annealing, as I have already discussed, are leading the charge, with hybrid approaches showing real promise today. There are significant hardware and other algorithm challenges as well, but progress is also accelerating. Most importantly, this is a field where students and researchers can make real contribution right now. The future of artificial intelligence will be shaped not just by machine learning alone, but by quantum enhanced machine learning. Because when we say machine learning, we are not talking about executing a specific algorithm, on a simple laptop or a desktop or a simple device. We are talking about providing n number of or n numerous inputs against those algorithms, and then expecting for the desired result from those algorithms, or desired result from those input parameters. For a human, for example, if you talk about if you give them 6 to 8 digit number and then ask them to make a combination of such numbers, it might take a huge amount of time, probably a number of hours, to make all the available combinations from those numbers. But for a computational system or a quantum computer to make those combinations from the given numbers, it's a matter of a millisecond activity. So just like how we are juggling the numbers to make all the different combinations, they are taking all the objects one by one, making the desired combinations, and giving the users the desired output at the same time. If we try to also have a recap from the yesterday's session as well, the roadmap which we have seen for the quantum computing engineers is going to be really unique, considering the classical computers versus the quantum computers. Laptops and all, which we have already seen, they were just using zeros and ones, but today the quantum computing systems, they mainly use qubits, and qubits, this is where the power of that engine, or that of that technique, it lies over there. So security, considering our yesterday's topic, security, and today's topic of quantum computing, mainly from the machine learning aspect, can makes together a complete portfolio from the practical implementation aspect for the research scholars. Thank you very much. Please feel free for any questions you might have, and then at the same time, you can get connected for any other doubts which you may have.
No, ma'am.
No, ma'am. Nah.
Sure.
ఇప్పుడు పిల్లలు ఉన్నారు. కనిపించారా?